Hello viewers, you're welcome to the third video on our ongoing class, Necessary and Sufficient Conditions for Laplace Transform. So in this third video, we are going to consider the same problem we studied in video 2. But this time around, we are going to take a step further by connecting the condition, which is called piecewise condition, and Laplace transform. So let's go back to this particular question. The question we're familiar with, that f of t is indeed a piecewise continuous. I think we verified that in our last video, in video 2, and then we concluded that the function is piecewise continuous based on 3 conditions. Condition number 1 is that the function is continuous within each subinterval. The problem is actually divided into 3 intervals, and each of them we can see that in the first interval, between 0 and 2, the function is indeed continuous. In the second interval, the function is discontinuous, but that discontinuity is something we can easily remove. We can remove it. And then the third interval, we also discover that the function is continuous. So based on that, we can say that the function f of t is continuous within each subinterval. That is where the name piecewise comes from. Piecewise means that it's partitioned into subintervals. And at the same time, the function f of t, it has a finite one-sided limit at the point of discontinuity. It has a finite one-sided limit at any point of interval. Okay, and at the same time, the third point is that the function does not have infinite discontinuities in interval. So at t equals to 2, the discontinuity we see there, it's finite. We come up with a number. So in that case, we can actually say that the function of it is piecewise continuous on the interval 0 and 5, as we've seen in video 2. So let's now connect that condition with the definition of Laplace transform, which is an integral from 0 to infinity e minus xt f of t dt. The function is indeed piecewise continuous, as we've seen. That's why we say that f of t meets this condition as shown above. We know that the function we are dealing with is actually piecewise continuous. So the second condition now is called exponential order condition. So this one here, we are still going to talk about it in the next video. Yes, it's something very important, because this condition is saying that the function of t we are dealing with, it must be less than or equals to a particular constant m multiplied by the exponential order, which is gamma, multiplied by t. That is, for this case, m must be a constant greater than 0. And even gamma must be a function greater than or equals to 0. Gamma can be 0, and it must be greater than 0, not a negative. There's nothing like negative order. Okay? So f of t is bounded, which I will still explain this later. F of t is bounded because if you look at the function very well, you see that it has a supremum and infimum. It has the lowest bound, and if you remember in MTS 102, boundedness of a function. So you can see that the function is indeed bounded. And at the same time, for t greater than 5, we can assume that the function is 0. So we can say that the function is of exponential order. So we need one more step, and that step is the fact that we need to evaluate the integral now, to evaluate the Laplace transform integral. And as you can see from the question, when the function is 0 to 2, f of t is t. So that's why you can see here now that e minus xt multiplied by t. Next is the second part, that is from 2 to 5. From 2 to 5, we can see that the function is actually 5 minus t. So we evaluate that integral as well. Of course, we know that to evaluate this integral, we need to integrate by parts. Yes, that is why you need to go back and then do some revisions on how to integrate by parts. But without any doubt, we know that these integrals, they are divine, they are valid. They are something we can evaluate. So that is to tell us that the Laplace transform indeed exists. So one thing we now notice is that when we're trying to evaluate the integral, you will notice that we didn't consider that of constants. Yes, do you notice that? From 0 to 2, from 2 to 5. Aha. So we did not consider the fact that what happened at 4. You know, what happened at 4 is a constant. Is a finite number, is a constant. So there's no way we can evaluate that integral at the middle, at that point of discontinuity. So we skip that. I think we can use that English. We have to skip that point of discontinuity. So, but most important thing now is that the Laplace transform converges due to the decay of exponential minus xt. You know, don't forget that minus in the power of exponential, it will make it to decrease. It will make it to decrease. So the Laplace transform converges due to the decay in exponential minus st. Although we also need to notice that, recall that f of t is also a piecewise continuous because it's continuous on some interval, and indeed it has a finite one-sided limit at t equals to 2. So this actually ensures that the Laplace transform integral is divine at the finite discontinuity at t equals to 2 and does not really affect the convergence. So thus we can conclude that the Laplace transform of t of that function that is piecewise continuous, it has a Laplace transform. Thank you very much. So let's proceed to the next video where we're going to focus more on the issue of exponential order. Thank you for watching. See you next time. Bye.